Right. Hi, everyone. There's a few more days to your O levels practical exam. All right. And we just want to take this opportunity to wish you guys all the best. All right. Stay calm. You already know what you need to know in order to do well for your practical exams. All right. So just stay calm and think carefully about what you have learned before during your lessons and so on. All right. And apply what you have been taught. All right. And I'm sure that you will be able to pass with flying colors. Right, but in any case, what we are going to do here today is that we're going to have a video, all right, for a quick revision of the different areas for your practical, all right, just in case there's anything that you want to recap on and so on. If at any point in time during the video, you find that certain explanation is not clear enough or you have certain queries, please do not hesitate to take out your phone, drop a message to your physics teacher, and we will respond to you promptly. All right? Now, so moving on, first thing, all right, this is what I'm going to go through for your experiment. All right? I think most importantly for your physics practical, the first thing that you must do is to read the instructions for your practical. This is extremely important. All right. Always read it first. All right. Make sure you know what the practical is asking you to do. Make sure you know what you need to find out. All right. In fact, I would even go to the extra length of advising you to read the questions as well. Find out what the questions are asking you for. All right, so you have a general sensing, oh, this is what I'm supposed to do before you actually start on the practical proper. All right, okay. Now, moving on, all right, moving on for your physics measurements itself, all right. Now, as I was saying, when you read the instructions, please follow the instructions. If they are saying that, oh, you have to come up with 2dp or 3dp and so on and so forth, follow the instructions. Always follow the instructions. All right, follow what is indicated in the question paper itself. All right. Now, but however, if nothing is indicated, all right, they expect you to know, then you should be leaving your measurements according to the tables shown here. All right. Most of it is quite straightforward. We already know this. We have seen this before. All right. Perhaps the only thing that you need to take note of is the one for your stopwatch. All right. I think most students tend to overlook this. We tend to look at the stopwatch and write down whatever numbers that we see over there. But however, the stopwatch actually measures to milliseconds and so on, I think. All right. And we don't actually, your measurement is not that precise simply because of your human reflex error. All right. So for stopwatch, you must remember when you're writing down your values, always write down to just 0.1 seconds. All right. Round off to the nearest 0.1 seconds. And that should be the measurement for your stopwatch. Right. Moving on. All right. When you are tabulating your data, all right. Now, when you are measuring your data, please take note. All right. Very, very importantly, if it's the same column, data in the same column, should always have the same number of decimal places. All right. So as an example, if you take a look at the negative example shown over here, yes, no doubt your measurement is accurate. It was a very nice value of 2. It's a whole number. All right. But if you take a look at the rest, all right, the rest of the readings have 1 decimal places. Okay. Now, what does this 1 decimal place actually tells us? It tells us the apparatus that you are using. So for example, if I look at this 1.2 cm, straight away I know you must have been using a meter rule. And then suddenly you tell me your value is 2. What does this 2 means? What apparatus were you using? Do you change apparatus in the middle of your experiment? All right. So because of that, please do take note to highlight the fact that, hey, we are using the same apparatus throughout. All right. The same column should always have the same number of decimal places. So that's why over here you notice that even if your experimental readings is a very nice whole number, please add the 0.0 behind so that you can standardize the number of decimal places for the entire table itself. As you can see over here, all right, usually they will also ask you for some sort of calculation. Now, if they ask you to find the average of 2 readings, again, the average will be, for example, your reading number 1 plus your reading number 2, and then you divide by 2. Now, in these situations, please do take note, your average should be the same number of decimal places as your original reading. All right, because the degree of accuracy is limited by the apparatus that you are using. All right, so in this case, for example, let's take a look at this. My first reading was 1.4, my second reading is 1.3. The average itself, all right, although yes, if you press a calculator, it will give you 1.35, but you have to remember, your apparatus is not that accurate. So because of that, all right, you should actually be recording it as 1.4, 1.3, and the average of 1.35 rounded off to the same decimal place should result in 1.4 as well. All right, so please take note of this. This is for average, all right, for average. Another type of calculation is where they ask you for example, over here, as you can see, take the V divide by the U. All right. Now, if it's taking V divided by U, or if it's, for example, finding T squared, T cubed, and so on and so forth, all right, then your calculation should be given to 3 significant figures. All right. Okay. So as an example, take a look at this. 1.73, 1.08, 0.739. All of these are 3 significant figures. But wait, just now I told you guys that if it's the same column, it should have the same decimal places. And clearly you can see in this case, A is not the same anymore. So what you should be doing is you should then look through the entire list after you have calculated whatever you need to calculate, look through the entire list again, add the zeros if necessary to standardize the number of decimal places. All right, so that they all have the same number of decimal places itself. Okay? So again, in this case, you are given 2 rules to follow. Number 1, all right, calculations should be to 3 significant figures. Number 2, in the same column, you should have the same decimal places. All right? Now, moving on. The purpose of doing an experiment is always to observe a certain trend, to identify a certain pattern. If you are doing an experiment where your results are fluctuating, going up for one, then going down, then going up, then going down, the experiment is inconclusive. All right, then what's the point of doing the experiment? O-level will seldom give you an experiment where it's inconclusive. So in such situation, then I would advise you, spot the difference, spot what is the 1 or 2 values that might be wrong, and perhaps to redo the measurement again. All right, so as you can see over here, right, in this case, we started with 1.2, suddenly it increases to 1.3, decreases to 1.4, decreases to 1.3, suddenly increase to 1.6 again. All right. So in this case, what I will do is definitely I will want to redo my readings even before I start on my graph, just to make sure that, hey, there must be something that went wrong. What is the error here? All right. In general, all of your experiment, if done correctly, it should have a certain pattern, a certain trend. It can be increasing trend, it can be a decreasing trend. All right. Okay. But there should be a trend. So please look out for this trend over here. Again, over here, summary. If your experiment, all right, your experimental results are going up and down, fluctuating all the while, it is inconclusive, double check your readings. All right. Okay. Moving on. Okay, and then based on your readings itself, they will be asking you to draw graph. And generally, there's 2 types of graph that we want to draw: the straight line graph, all right, or the curve graph. Okay. Now, for straight line graph, please take note if they ask you to describe. So usually they tell you to do an experiment, then they say, hey, you know what? Plot a graph of this against this. And after you plotted the graph, all right, the next question that follows is, what can you identify about X and Y? All right. Then you can say that, oh, the relationship Y is linearly related to X. All right. Y is linearly related to X. That means that it's a straight line. All right. And if it's a curve, then of course it will be the other way around. Y is non-linearly related to X. All right. Okay. So it's either linearly related or non-linearly related. Right. Now, and also for the plotting of graph itself, okay, usually teachers, we like to refer to this acronym known as SLAP. All right, and each of these letters stands for 1 point that you need to consider when you're drawing a graph. The first one, which is S, stands for scale. All right, the scale of your graph. Okay, the scale of your graph. Okay, so for graph itself, please take note that usually our plots should be 60%, minimum 60% of the graph paper itself. Now, take note, for this 60%, I am looking between your first and your last plotted points. So as an example, students like to give me this first point, all right, last point, and then after that they say, oh my gosh, it's not 60%. So what they do is they draw a very, very long line. Now, please take note, in this case, again, my 60% is between the first point and the last point, all right? I do not care how long your line is. So in this case, I will still penalize you, all right? What you should be doing instead is that you should be doing the first point over here, the last point over here as an example. I will look at it horizontally. Is it bigger than 60%? And then after that, I look at it vertically. Is it bigger than 60%? All right, and that's where I assess your scale of your graph itself. Okay, now moving on, please also take note for your scale itself, choose an appropriate scale. All right, because the scales are according to the number of boxes, and usually we write down one number every 10 boxes at least. All right, so we would want to stay away from numbers like 3 and 7. All right, because you take 3 and you divide by 10 boxes, each box is 0.3. It's a very difficult number to work with. So usually we tend to stay to these 4 numbers that you see over here. 1, 2, 5, and 10. These are the numbers that is easily divisible. All right. Okay. And also please remember for physics, all right, there's no need for us to start from the origin, which is 0, 0. We do need to start from that. All right. So read your question. If the question asks you for y-intercept or x-intercept, then yes, please start from 0, because if you don't have 0, you cannot find the intercept. All right, okay? But otherwise, you are free to start your y-axis from any number. For example, my y-axis starts from 10, my x-axis starts from 3. It's possible. All right, so because of this, please label what is the number that you are starting from. All right, so in this case, for my example over here, I'm starting from 0 and 0. All right. And I want you to pay attention to this. You notice that the number of decimal places is very different, because the number of decimal places should be according to your table of values. So for my y-axis, because in my table of values, my y-axis are all 1 decimal place. So therefore, my origin also 1 decimal place. All right. And for my x-axis, all of my values are to 2 decimal place. So my origin also 2 decimal places. Again, this is not a fixed rule. You do not start, it's not compulsory that y-axis must be 1 decimal place. It should follow your table of values itself. All right, so please take note, always refer back to your own table of values. Okay, now for the second letter in the slab is actually your L, which stands for line. All right, which stands for the line itself, your best fit line. And I'm sure by now all of you know how to draw a best fit line. Roughly, you know that the line should be in the middle of all of your points. There should be roughly equal number of points above the lines and below the lines. All right. And the sum of the distance over here, although you don't actually measure it, all right, the sum of the distance below the line should be equal to the sum of the distance above the line. So that's how we roughly know that whether it's a best fit line or not. All right. And also, please take note that your lines itself should extend. You should extend your line. Don't just draw from the first point to the last point. You should go beyond, all right? Extend it beyond your first and your last point, okay? You will be good if you can draw it such that it cuts the axis itself, all right? So just draw it and extend it all the way to the axis itself, okay? Moving on, the next part of the acronym, A, stands for axis, as you can see at the side over there. So please label your axis. Now, this slash over here, it means in terms of. So for example, over here, it will be measurement of L in terms of cm. All right. So you must always have that slash. As an example, temperature in terms of degrees Celsius. All right. Time in terms of seconds. All right. So you must always have that slash over there. All right. So first thing, please remember, label your axis. All right. Both your x and y axis, they are extremely important. All right. Okay. Moving on. Before I move on, also please remember, you must draw your arrow. Your arrow head is very important. All right. Sometimes students, they just draw the line itself, but they forget about the arrow head and then they get penalized. The arrow head represents, increasing numbers. So please make sure you draw your arrow head itself. All right. Okay. Moving on. Next part, lastly, the P stands for your plot, which is basically your points itself, all right, your plotted points. Now, something very important, please remember to mark all of your points with a cross, all right? Mark all of your experimental points with a cross itself, all right? And of course, follow your table of values accurately. Your examiners will be checking your points very carefully. So please follow your table of values very accurately. All right. Definitely, please avoid the situation where, for example, my lines are all very nice. It's like 1, 2, and 3. All right. But I've got the fourth point over here that's not in the line itself. All right. Please do not be tempted to change. All right. Don't go and change the value. Say, oh, you know what? Never mind. I just draw it. I just erase it. I just draw it over here, because your examiner will definitely be referring to your table of values as they check your plotted points itself. All right. Moving on. Next part is once you've plotted the graph, usually they'll ask you for the gradient calculation or to find a certain values. Say, for example, what's the value of x when y is equal to something. All right. So let's start with gradient. Now, gradient itself, please remember the most important thing you must have is your gradient triangle. All right. And what exactly is your gradient triangle? Your gradient triangle is basically referring to this dotted line over here. All right. So to calculate gradient, we know that we need 2 points. All right. So try to find 2 points that is on your best fit line. All right. On your best fit line, but not experimental data. So as an example, these are my 2 points over here, as you can see. All right. Now identify that point with a dot. All right. With a dot over here, and also write down the coordinates for the examiner. All right. For both points. So a dot and also your coordinates over here. Okay. Then draw the gradient triangle from one point to the other point. All right. Please take note, for all construction line, such as your gradient triangle, it should be a dotted line. All right. The only solid line should be your graph itself. Okay. Now, so after you have gotten the coordinates, you have drawn the gradient triangle, the next thing that you need to do is, of course, to use a formula. So you're using the same formula as that you use in math itself. So it's y2 minus y1 over x2 minus x1. All right. Do your calculation accordingly. Please round off your final value to 3 significant figures. All right. Because this is a calculation after all. All right. And just a gentle reminder, this is physics. Everything should come with a unit. All right. Everything should come with a unit. Okay. So in this case, it's y-axis divided by x-axis. So it's going to be cm divided by seconds. All right. Now, the only exception is when your x and y, they have the same unit. All right. So, for example, your x is in cm, your y is in cm. So, your gradient itself will then have no units. But that's the only exception. Otherwise, always double check. There should be a unit itself. All right. Moving on, the other type of question that they like to ask you is find the value of this when time is equal to 10 and so on and so forth. So what you do, right, is as an example, in this case, find the value of t when L is 13.5. The first thing that you need to do is find out where's 13.5 on your y-axis, write it down for them. All right. Second thing, draw a dotted line, a horizontal dotted line, all the way to your best fit line. All right. Thirdly, from your best fit line itself, extend the dotted line until it reaches the other axis. So in this case, downwards until it reaches the the x-axis. And lastly, write down the value of the x-axis for them. All right. So these are the 4 things that you need to do in terms of showing your workings when they ask you for a certain value itself. All right. Okay. Now, just a gentle reminder: all of your labeled values must be the same number of decimal places as per your axis itself. So if it's supposed to be 1 decimal place, please make sure that it's 1 decimal place. If it's supposed to be 2 decimal place, make sure that it is so as well. Right? Moving on. Okay, the following segment is on sources of error and how to improve the accuracy. So it's basically some suggestions and so on. Now, for the next few slides, I think that there's a lot of data over there. I'm not going to talk about most of them. I'm just going to leave it there for maybe around 3 seconds or so. If there is a need for you to pause the video so that you can read it in detail, so they can take down some notes, please do so. All right, just pause it, and then when you're ready, just let it play again. All right, okay. So these are some sources of errors that, if you are not too sure and you can actually take note of them. And if you are doing the same experiment, you think that, hey, this source of error seems to be applicable over here, then you can list it down in your answers. All right. And most importantly, nowadays exams has increasingly they are asking you not just for source of error, but they are also asking you how to improve on the source of error. All right. So you please do take note. In addition to this column, all right, please take note of this column as well. All right. Okay. Not just what is the source, but also how to improve the accuracy given that you have the source. All right. And also, please do take note. Usually, when they ask you for source of error, right, they will ask you, hey, how does my source of error, how does this source of error actually affects the reading? So, for example, what is the source of error? Oh, there's a human reaction time. It's no longer sufficient to just say human reaction time. You must also tell us how did this human reaction time actually affect your data. All right, okay? So please explain a little bit, as in this case, explain that, hey, the time recorded may then be larger than usual. All right? Okay, moving on. In general, this is a very common suggestion that you can actually use in a variety of experiments. Basically, take more readings, all right, and then find the average. Don't just say take more readings and full stop. All right, you must tell them to take the average, otherwise they will penalize you for it. Okay, so this is something that's applicable for most experiments. Okay. Now, but as usual, let me just remind everyone, the list that was shown before, it is not an absolute list. All right, doesn't mean that it's stated there means you can definitely use it for your experiment. Please do consider whether it's applicable or not in the first place. All right. Okay. Now moving on. What to take note of? Some precautions when you are using the apparatus itself. In general, there's two types of precautions that we have: precaution against parallax error, precaution against zero error. All right. Now, please do take note. These precautions cannot be stated as a source of error. All right. It is a precaution because you have already been taught how to compensate for it. All right. So if you say it as a source of error, then the examiner will be thinking, does this student know what he's talking about? Doesn't he know that zero error can be compensated for? All right. Okay. So please consider it accordingly as well. All right. And again, if you need to, please pause the video over here so that you can read it or you can take down some notes on this. Next, talking about the pendulum itself. All right. Okay. So these are some precautions to allow the pendulum to hang freely and to place the ruler parallel to it. All right. Okay. Another precaution that you might want to take note of for pendulum, but it's not shown over here. All right. Usually they will ask you to displace the pendulum at a small angle. The angle of displacement for pendulum, right? So for example, if let's say this is the rest position of the pendulum itself, the displacement angle is usually this one over here. So this is your displacement angle. All right. Now, usually for displacement angle, it should be a small displacement. All right. Please don't go and lift up your pendulum until it's 90 degrees and then you let it swing, because then the oscillation will be very erratic. Okay. So please, one of the precautions, as I was mentioning, one of the precautions that you can say is that ensure that the displacement angle is actually small. But do take note, if this has already been stated in your practical instructions, all right, in your practical list itself, please do not write it down again, because you shouldn't be quoting something that they have already told you to take note of. All right. Okay, and also you have that for your measuring cylinder as well. All right. Okay. For those of you who can't remember your meniscus itself, all right. So if let's say your measuring cylinder reads like this, the bottom of a meniscus would refer to this portion here. All right. So please read it accordingly. All right. And of course, lastly, the timing the periodic motion of a pendulum. All right. Okay. This part over here, please take note. Okay. Students like to. So one of the I think common mistake or things that students overlook is that we tend to start the stopwatch once we let go of the pendulum. But honestly, right, the first few swings of the pendulum are usually not as regular. So what we need to do is usually start the pendulum first. So let me just write it down. Start the pendulum. So let go of the pendulum. All right. And you don't record it first. All right. Step two, you let it swing. All right. Let it swing for one or twice. All right. Let it swing for maybe 2 or 3 times. All right. And then when it reaches the point of the oscillation that you want, so for example, when it reaches the highest point, let's say A, B, and C, right? So when it reaches A, then you start pendulum. Oh, I'm sorry, not start pendulum, but start the stopwatch. Start the stopwatch when it reach A. Okay. So in this way, we avoid the timing for the first few swings. We make sure that the timing is only when the oscillations are regular and steady. All right. So this is what it means. And for lenses, all right, quite a number of precautions that you can write down. You can take note of. All right. So these are all things that you can actually write down. But of course, please think whether it's applicable to your particular experiment. All right. And for your mirror or your glass block, all right, I think one of the most difficult thing for us is to make sure that it is fixed, which is why they always ask you to draw the outline of the glass block or draw the outline of your mirror itself, all right? And the purpose of drawing the outline is so that when you are repositioning the glass block, you can fit it back exactly in the same spots, all right? But in any case, this is one of the precautions that you can write down. All right, and then for your optical pins itself. Okay, when doing experiments involving optical pins, I think one of the most important thing is that you have to make sure that it's vertically upright. All right, because one of the issue is that sometimes we tend to put the pin such that it's tilted at a very slight angle, but that will still affect the readings. So just make sure that the pins are placed vertically upright. And of course, these are for the other apparatus that we're using. All right. For those of you who forget, the laminar is basically your cut shape, the odd shape cut. All right, that we had to measure and find the center of gravity. All right. So it can look something like this as an example. All right. Okay. So it's the one where we want to find the center of gravity. I think one of the precautions that you might want to think of when you're poking the holes in the cutter, although your holes should be near the edge, but please don't poke it too near to the edge. All right, because sometimes students poke it too near to the edge and then they accidentally pierce it and then it breaks the cut and they have to redo the experiment again. All right. For temperature itself, I think one of the things that you have to take note of, another precaution is to ensure that the bulb of the thermometer right? So this is one more precaution that you can actually take note of. And of course, the reason for this precaution is so that you are measuring the temperature of the water and not the temperature of the beaker itself. All right, and then for electrical circuit, okay, I think the most common one that we always use is to switch it off when you're not taking any readings, so that you do not increase the temperature, overheating, right? So that you do not increase the temperature, because when you increase the temperature, it will also increase the resistance. All right. Again, increase in temperature will affect the resistance and therefore will cause the current to be lowered. All right. And even affect the voltage. Sorry for that. All right. And the last part over here is for your resistance wire. All right. So we usually say, you have to tighten the wire, you have to make sure that it's uniform and it's properly taped, right? So some things that we usually tend to say it would be, in terms of sources of error, would be the kinks in the wires, right? I think another precaution that you might want to think of over here is that your jockey should be perpendicular to the wire itself. So if this is your wire and this is your jockey, as an example, it should be perpendicular instead of doing this. All right, and the reason is because we want to ensure that the point that the jockey is supposed to be touching is accurate. All right, because if you were to move this downwards, you will be touching the wire over this entire area rather than a sharp point. All right, and I think that's more or less it for the physics practical, at least the things that I can remember at this point in time. Again, like what I said just now, if there's anything that you're not too sure about, please drop a message to your teachers. All right. Physics practical is actually a very easy practical to do. All right. You just need to follow the instructions. All right. Stay calm. All right. I'm sure you'll be able to do well. Okay. So key idea over here. Number one, stay calm. Number two, follow instruction. Number three, do well. It's as simple as that. All right. All the best. Okay. Thank you.